Welcome to the Australian Water School, the home of demand-driven industry design training for the global water sector.
Hi everyone, and welcome to another webinar in the highly successful series presented by the Australian Water School. We're so glad you're here today. Delighted to see so many for this webinar on MODFLOW 6 and FloPy, presented by Vincent Post and Mark Backer. My name's Trevor Pillar and I'll be chairing today. There is a large number of people. We'd encourage you to get questions and comments in early on the Q&A line, but look at that, every continent represented. It's terrific. Thank you so much for joining us. Here we are. Vincent, good to see you, Vincent, once again. I think I've known you for 20 or 30 years at Flinders University. That'd be right?
Absolutely. I think we first met in 2004 at a Freak Sea course in Brisbane, if I remember correctly. Yeah.
Yes, I do remember. That was a stunning course. And Mark, your colleague Vincent Mark is with you today, both from Netherlands. Mark, in Netherlands?
That's right. Yeah, we're both in Holland. It's still pitch dark outside here. It's early morning, but
oh wow, It's dark outside. It's about 3:30 where I am, and it's only 5 degrees here, so getting close to where you are there. Hey, this is great. Mark's from the Technical University at Delft. Vincent's from Edinsi Consulting Groundwater and also Flinders University. I'll let them maybe say a bit about themselves as they come on board. It'd probably be the best way to go. That would help us get right into this immediately. But I can assure you there are decades of deeply a rich understanding of groundwater modelling with us today, and I know you're not going to regret being on board, everyone. So you did a wonderful job with those surveys. Can we have a look at those now, do you think, Joel, Renee? That'd be great. Any comments as we go through, Vincent or Mark? Please do. Commercial and consulting, you expected probably the larger number there.
Yeah, that's about half of them almost. Yep, that looks good. And then a third from academia, that's nice.
Yep, and the second one, never used MODFLOW, is higher than what I expected, but that's good.
Yeah, a couple of people have used the GUI.
Yep.
Quite a few people with Python experience. That's excellent.
That's great news, everyone. That helps Mark and Vincent highly.
Yeah, if you have to start this from scratch, then it will be certainly will be a challenge. But if you have some prior experience up your sleeve, that is definitely good. And then we see that quite a few people that have some Python experience already for a couple of years. Yep.
No, very good. Thanks everyone for that survey. It just gives us a bit of a heads up as we begin this webinar today. Righto, I won't say any more. Put your comments and questions in early, get them in often, of course, though. But right now, I'm going to hand straight over to Mark from Technical University in Delft. And then, Mark, you'll hand across to Vincent. But keep your questions coming, everyone. We'd love to have them. Vincent's on board at the Q&A line, and then vice versa. Mark will be on that Q&A line when Vincent's speaking. All right.
All right. Good morning, everybody. Also from my side, I have a couple of introductory slides. And I can also introduce myself a little bit. I've been using Python for since last century, really. And I've been doing groundwater modeling also since last century. What's with MODFLOW, also other programs. And what we want to talk to you about today is how to use MODFLOW 6 and FloPy. If you have never used MODFLOW, it's a finite difference model. And that basically means we take our aquifer and we divide it in Lego blocks, and we calculate a head for every Lego block in our system, and then we calculate the flows between the Lego blocks. And of course, the smaller you make the Lego blocks, the more accurate solution you get, but also the longer it will run on your computer. So it's a trade-off. And we're going to have to define boundary conditions where the Lego blocks end. We have to specify something, what's happening there, like a constant head or a no flow. Now, MODFLOW has a long tradition or long history. It stands for modular flow. It's very well written by the United States Geological Survey. It's freely available and very well documented, which is part of the reason it's so popular. It started in the 1980s. The first big popular version was MODFLOW 88. And then about every 5 years, they came out with a new version until MODFLOW 2005, which for a long time was the industry standard. And then around 2016, they introduced what they wanted to call MODFLOW 6, and they have called it MODFLOW 6. MODFLOW 6 is a big change as compared to MODFLOW 2005. That's maybe why it took so long to get out. As compared to MODFLOW 2005, we can do irregular grids. As you can see the picture in the lower left-hand corner. We can link models, so you can add a surface water model to your groundwater model and solve them simultaneously. They're very clever solvers, like the Newton solver. And it says here, and more, like it can also do transport in there now. There's not a separate CWAT anymore, for example, to do density-driven flow, but you can do that within MODFLOW 6. We won't get into that in this workshop. We'll cover the basics. But those are the capabilities of MODFLOW 6. But also, and that's what it says there, there's a new syntax. It's not backwards compatible with the old MODFLOW. Quite a few things look like what they were, but they are different and hopefully better than they used to be. Now we can run MODFLOW, and that was one of the questions in the questions you got at the pre-webinar questions. And most people use MODFLOW or have used MODFLOW using a graphical user interface, a GUI. And popular ones are Groundwater Vistas, DMS, Visual MODFLOW, and Model Muse, and there are many more. But about, what is it by now, Vincent? About a little more than 10 years ago, Vincent and I said, well, we wanted to be able to write a script to run MODFLOW. So what we designed was a procedure to do that, and we ended up calling that FloPy, which means that it's a package that can write scripts to generate input files for MODFLOW, which are just all text-based files, which have with lots of numbers in there. Then run MODFLOW and then read the output from MODFLOW back in and try to visualize and analyze. The major advantage of that is that it is fully reproducible. You don't have to remember which buttons you have clicked. It's also less error prone. You don't have to check all the boxes to make sure you click the right boxes. You can read your file and see what you've done. So it's fully documented in what you have done. And you can do anything with it because you have the whole Python ecosystem behind you to do your analysis. Now, once Vincent and I started FloPy, we implemented the packages and features that we like and that we have used or that we wanted to use. But there were very many more packages that we didn't use or that we didn't want to use. So the USGS, but the USGS got on board. They were very interested in what we were doing, and they pretty much took over, which was great. So they implemented all the MODFLOW options that there were available. And quite frankly, I haven't written a FloPy script, a FloPy program line for a long time. The USGS is doing it. I'm just now being changed into a user, which is great because I think we can do a lot with that. Couple things about FloPy and about MODFLOW. Once we moved to FloPy, we quickly realized that we had to use the Python numbering system, which means everything starts at 0. So we have layers that you've seen here. This is can we see? You cannot see my mouse. You can see we have 5 layers here, numbered from the top down: 0, 1, 2, 3, 4. And then we have the rows and the columns of the system numbered as well. Of course, in MODFLOW, we have aquifer 1, 2, 3, 4, but we in FloPy they're called 0, 1, 2, 3, and that's kind of something you have to get used to. But it also avoids a lot of mistakes because in Python things start numbering at 0. Here again, the conventions we have for that. Here we have a two-dimensional grid with 6 rows from 0 to 5, up to and including 5, and we have 9 columns. The columns are numbered from left to right or from west to east, but the rows, strangely enough, are numbered from north to south. It's like the numbers the rows are numbered in a spreadsheet. And there's a couple other conventions you have to realize when you use FloPy. You have to use consistent units. You actually specify somewhere in MODFLOW what the units are, but it doesn't use that. It assumes you are consistent. What we will be using today, and what I always use in practice, is meters for length and days for time. And the other thing you have to realize that it has a convention for discharges and fluxes. When water goes into the model, it's positive. When water is going out of the model, it's negative. As long as you know what it is, that's the way we're going to run it. Now we're going to do FloPy scripts, and all our FloPy scripts are always implemented in Jupyter notebooks, which I hope many of you have seen. So the entire workshops that we'll teach, we'll go through these Jupyter notebooks where we'll have explanations, code, and examples, and the output all in one document. And I've just switched to that right here. This is the notebook we'll go through today. Now we have a lot of stuff in here to give you an overview of what can be done with FloPy and MODFLOW 6. So we won't be able to go into every detail, but we'll do that during the course. And what you see here is a Jupyter notebook. Here on the left side, this is actually Jupyter Lab that we're running it in. Here on the left side, you can see my mouse now, is the table of contents. So that's kind of useful today to look at where we are in the modeling process. And here on the right side, you see all the code cells. So I'm going to sit in those code cells and run them one at a time. And I'm going to have to run the first few where I import the packages or the libraries, if you wish, to do that. And let me first introduce to you the problem that we're going to solve today. As an example, we have a square model consisting of 4 layers. The square model here has a river here on the side in blue, where the head is 58 meters. The other sides are impermeable. The model is 5,000 meters by 5,000 meters. And there are 3 wells located in the model, wells 0, 1, and 2, right? Start numbering them at 0. They're equally spaced, and they are about 500 meters away from the river. And they have equal discharge. So if we scroll up, you can see that the cross section of the aquifer system, we have 4 model layers, 0, 1, 2, and 3, where layer 1 is a low permeable, an aquitard, if you wish, or a leaky layer. So we actually have 3 aquifers and 1 leaky layer, or you could even say we have 2 aquifers, but the bottom aquifer consists of 2 layers with different properties, and the wells are all screened in layer 2. Remember, that's the 3rd aquifer, right? 0, 1, 2. So this is the vertical cross section. And on top of the system that causes flow is recharge, and we give that the symbol capital N that you see right here. Now, briefly look at what the model parameters are, right? The length of the model is 5,000 meters. We're going to model this with 100 columns and 100 rows. So ncol, for those of you who have just used MODFLOW before, that's the name they give it, and nrow are both 100. So we can calculate the length of the cells in the row direction and the length of the cells in the column direction. They are 5,000 divided by 100, so they are 50 meters long. We have 4 layers. The top of the system is at 60 meters. And then we have to define the bottom of each layer. So the bottom of layer 0 is at 40, layer 1 is at 35, then 15, and 0 is the bottom of our model. We have aquifer properties. The horizontal hydraulic conductivity is in the top layer is 20 meters per day. Then we have the leaky layer, the aquitard, it's 0.01 meter per day, or a standing meter a day. Then the bottom aquifer consists of 2 layers. The top layer of that is 10 meters per day, and then 5 meters per day in the bottom layer. The vertical hydraulic conductivity, we've picked the same in those layers. We could have picked something else, but they are the same right now. And the porosity is 0.3, and we need that porosity later on when Vincent takes over, and we're going to look at Pathlines through the system. Then finally, the boundary conditions. The head in the river, I already mentioned, it's 58 meters, so it's slightly below the top of the aquifer. It means the top aquifer is going to be unconfined. The discharge of each well is 3,000 cubic meters per day. That comes down to about 125 cubic meters per hour. And notice the minus sign, right? Because we're taking water out. And the recharge on the system is 0.5 millimeter per day, or converted to meters per day. It's 5 times 10 to the power minus 4 meters per day. That's the recharge, which is going to be the same in every cell for this. So I'm going to run this cell. And now we're going to create a simulation. And I'm going to shift back to the table of contents here. When you build a MODFLOW model, there's a lot of steps you have to go through. And the steps are shown here. We first create a simulation where we have to define a number of things, and then of which the last one is a groundwater model. And once we've built the defined the groundwater model, we can add packages to that groundwater model, like the discretization and the wells and what kind of output we want. That's the way MODFLOW 6 works, right? And that's a bit different than the way all the older models worked. So we start out with a simulation. And for that, we've imported FloPy all the way at the top, and I'm going to scroll back to that all the way at the top. We've imported FloPy here in the very first code cell, and we called it FP. So we don't have to type FloPy all the time anymore. So all the FloPy commands start with FP. And FP, and then we're going to run the MODFLOW 6 sub-package of that. There's also other ones, and we're going to create a simulation. And the command in the MODFLOW or in FloPy is mf simulation. We have to give it a name. We have to tell it we're running MODFLOW 6. We have to tell it where MODFLOW is located on our computer. And we'll go into detail in that in the workshop. That's always difficult to define, but you have to install the MODFLOW executable on your machine to be able to run it, obviously. And we have to tell it what subdirectory we use to store all our MODFLOW files once we run the model. Now we've created a simulation. And what's important here is that the simulation is stored in a variable, and we've called the variable sim for simulation. Now we're going to add to that simulation two things. We're going to add a time discretization, and or three things actually: a time discretization, an iterative model solution, and a groundwater flow model. This is what we do before we even get into the groundwater flow part, right? The time discretization. Well, we're going to run a steady state model all the way at the end today. Vincent will make a transient for you. But for a steady state model, we have to define the length of the period, the number of steps, and the time step interval 1 because it's steady. But you still have to define it. So we do that, and then we add it to that simulation that we call sim. So that's the very first argument here of the MODFLOW TDIS object. That's the time discretization. We also have to tell it how to solve the system, and there's many options in MODFLOW 6, but we're going to use the simplest one, and it's called simple. It doesn't get easier than that, right? And there's one variable here that we actually define, and it's commented out, as you can see, for those of you who are good with Python. The little hash mark means that that line is commented out, and maybe Vincent will turn it on later on to get a more accurate solution, but quite frankly, it's pretty accurate with this default settings. So we're going to add this iterative model solution again to this sim, to the simulation. We've done that, and then finally, we're going to add the groundwater flow model. The groundwater flow model is shown here. We're adding it to the simulation. We give it a name, and we've earlier on defined that name in one of our first cells, and we tell it what name file to use, and we also tell it to save the flows, right? We don't want it just to save heads. We also want it to save flows between cells, so we can actually do Pathlines. Now we have a groundwater flow model, and that groundwater flow model is called GWF. And we're going to add to that groundwater flow model. I'm going to scroll back up here in the table of contents. We're going to add packages to the groundwater flow model. And we're going to add a number of them, as you can see them all here, and we go through them step by step. So I'm going to scroll up and start adding packages to my groundwater model. And the first thing we're going to add is the discretization, right? We're having a bunch of cells that we're going to use. So we use the MODFLOW GWF, groundwater flow, this object, and we're going to define what our discretization is. First of all, we'll tell it, we're going to add it to the groundwater flow model that we've defined, and we call it GWF. And then we tell it length units to use is meters. Again, MODFLOW doesn't really use that, but it uses the word meters in its output files and whenever it sees a length. So that's nice if you look at your output. We define the number of layers, which we had 4, the number of rows, which was 100, the number of columns, which was also 100, the length of the cells in the row direction, and the length of the cells in the column direction. I think they were all 50. the top of the model, which you picked at 60, and then the bottom of each layers, which are 4 values with the bottoms of each of the layers. That's our discretization. Then we go to the next property, the next feature we're going to add, and that is the node property flow, where we define the hydraulic properties of our cells. We use the groundwater flow NPF, node property flow package. We add it to our groundwater flow model, which we call GWF. We tell it that it should save the specific discharge between cells. We give it the cell type, and if I can look at what I put in here, it has 4 numbers, 1 for each layer, and the top layer is unconfined, and that has the cell type 1, and the other layers are confined, which have the cell type 0. Then I give it the hydraulic conductivity, K horizontal for all the cells, and the vertical hydraulic conductivity. And the keyword for that in FloPy and in MODFLOW 6 is K33. It's kind of a cryptic name that comes out of TensorFlow. You can actually define hydraulic conductivity tensor if you know what that is. And so, but we only have to define the vertical component. So I'm going to run that cell. We go to the next one. The next one, we're going to add the initial condition. Now you might wonder, we have no initial condition, it's steady flow. That's correct, but it's going to have to iterate for the unconfined flow in the top aquifer, where the saturated thickness depends on the head. So we have to start at a value, and that's what you define here. Vincent will also use it later on when we actually do a transient simulation. So we use the GWF groundwater flow initial condition package. We add it again to our model that we call GWF. And the starting values are all the same, and they're equal to the head in the river, which I think we made 58 meters, right? So we start at 58 meters everywhere in our iteration, in this case, for the steady solution. Then we have to specify heads in the specified head cells, and that's the river. So we had a river on the right side and the head in the river, and all those cells in all 100 rows, but the very last column of our model has the value of 50. And we do that with the CHD specified head package. I'm sorry, I wonder what the C stands for. Which means that you specify all the cells by layer, row, and column in our model. I'd be doing a MODFLOW 6 model with a regular grid, so it makes it somewhat easy. So we have layer 0. The row goes from 0 to 100, looping over all the rows. And the column is the very last column, and the very last column is number 99, right? And call, which is 100 minus 1, it's number 99, because the very first column is number 0. And then we tell it, all right, all those cells have a head that's equal to the head in the river, which was 58. So we add that to our GWF model. Then we have a couple things left. Let's look here at the left side. We have done the first 4 things. So now we have the last ones. We still have to add recharge and wells, and then specify something about output. And then we can finally run the model. We're getting close. The recharge. We use the GWF RCHA aerial recharge package. We add it again to our GWF model. We tell it what the recharge is, and we have the same value in every cell, but you could have different ones in each cell if that's what you want. We also give this package a name so that you can find it back in the budget file later on when we look at the total water balance. So I'm going to run that one. And then finally, the last thing we have to add is we have to add the wells. We have three wells. They are all in column 90. Remember, that was 50 meters away from the river. And we've put them in row 40, row 50, and row 60. So they were somewhat symmetrically located. And they're all in layer 2. So layer 2, those 3 rows, and the column is always number 90. And the discharge of the wells was 3,000 cubic meters. Q well was defined as minus 3,000, actually, because we're taking water out. Once we've made this little dictionary or this little list, we add it to the GWF model, and we specify the values that we just defined in the cells below. So we run that. We've added the wells to the MODFLOW model, and we have to finally give it some output control. We tell it the GWF model. We want to save all the budgets in the CBC file, the cell-by-cell flow file. We save all the heads in the heads file. We define all those. We add that, and now we are actually done. We could run the model now, but let's quickly check whether we did it right. And I don't have much time to go into that. Vincent will talk a little bit more about the plotting, but we can make a nice little plot. This is what our grid looks like. The blue cells that we've defined here are specified head cells, and they look indeed exactly where we want them. That's the river. And the red cells is where we have wells. Those are in here as well. So it looks like we did that correct. And we can also make a vertical cross section of that. So this is a vertical cross section. You see our 4 layers. The river is screened penetrates the top layer, and the wells are screened in layer 2, which is really the 3rd layer, right? 0, 1, 2. And this takes a little time to get used to. So it looks like we're good. Let's try to run it. There's simulation we call sim, and we have to do 2 things. We have to write the simulation that writes all the MODFLOW input files, and then we have to run the simulation. And then we get a lot of scrolling on our screen. This is all the messages MODFLOW gives back and telling us what it's doing. So I'm going to through that. It shows here nicely which MODFLOW 6 version I have installed on my machine that was compiled earlier this year. It's version 6.30. It has a disclaimer from the USGS. It tells us when it started, but the most important thing is at the end, and it's kind of hard to see now because I have this little block here. It says normal termination of simulation. And that's great because that means, there we go, that means it worked. Right? If it does not end with that, then you're having an error somewhere. And we'll get into that in the workshop a little bit on what to do. Okay, so great, it done. I want to see something, right? What MODFLOW did, it wrote heads to a file that has an extension.heads. So what we have to do is we're going to have to read those heads back into the Jupyter notebook and then try to visualize them. The way that works is that the FloPy has a package called utils for utilities, and you can open a head file and give it the name of the head file. That head file object is returned, and I'm calling it here HDOBJ, and then I can ask it object anything I want. Like I could say, get me the data for layer number 2, MODFLOW layer number 2, right? So that is the 3rd layer in our MODFLOW model. And I'm storing all those heads, which is then a grid of 100 by 100 points in a variable called head, and I can ask it what the minimum and the maximum values are. And I find out the minimum head in my model is 50.6. That's got to be in one of those well cells. And the highest head I find is 65.98, almost 66 meters. So what I can do now is I can contour my solution, make a head contour map. To do that, we use the plotting features of FloPy. FloPy has a package called plot, fp.plot, and it has a plot map view object that you can make. So if we call that and we give it the name of our model, and the name of our model was GWF, we get back a plot map view object, PMV, and that we can use to plot things. And the 2 things we want to plot is we want to plot an array that gives us a color plot of the heads, and we want to contour the array. And that's what I'm doing here, contour the array. I say, okay, the array is the heads, which I just read in. These are the heads in layer 2, where the wells are located. I give it the levels I want to see, starting at 50 with steps of 1 up to 70. And I know it doesn't have a 50, but Python nicely skips over that. And the first one it will find is probably number 56, right? That's the lowest head we had in the model. And it goes all the way up to the highest one it finds, or 70, which either way, it's which one it finds first. Let's run that. And there is our figure. That's what I wanted to get to at about 7:30 my time. So that's about right. So let's look at what we have. Here is our model. It's 5,000 by 5,000 meters. These are the heads in layer 2. I've plotted them in 2 ways. I've color coded them. from yellow, which is about 65, which is on the left side of our model, to 55 here in the middle. That's the darkest color you see. That's at the wells. 58 is right here at the river. And on the same plot, I've also drawn the contour lines. It makes it a bit easier to see, right? So this is the 65 line, the 64 line. So remember, the north, west, and south boundaries are impermeable. The east boundary is the constant head river, but this is layer 2, so it doesn't look like constant head because it's only constant head in the top layer, which you could also have plotted. And you see the drawdown at the 3 wells that we've specified, where we're taking 3,000 cubic meters per day out. Good. That was a lot of you to show you. I know I went through this fairly quickly, but this is an overview in this webinar of what we can do. And I want to stop my part there and see if Vincent is still with us, probably busy answering questions. Vincent and Trevor.
Yes.
Are there any questions in the chat we need to discuss here, or is it time to move on to the second part?
No, there were a couple of questions, and I think in the interest of time, I'll just continue because I've been able to keep up and answer the all of them. And I just see a question here popping up from Abibi, who is asking about what about the water balance? I think that provides the perfect segue to the part that I'm going to be presenting, because that is exactly the thing that I was going to start with. So thanks, Mark. And it was a great overview, I think, of putting together a MODFLOW model with FloPy. And it may look scary if you're not familiar with Python, but if you have some experience up your sleeve, like Mark and I, then you will see through the code and the model will just pop up in front of you. And yeah, that's maybe some professional, anyway, never mind. I'm going to continue with the example and show you another feature that we have in FloPy, and that is the capability to read the cell budget output file. And if you've worked with MODFLOW before, you may be familiar with the software called Zone Budget, where you can do water balances for the entire model or parts of your model. And if you use FloPy, you have a lot of these capabilities that are in the Zone Budget software. You have them at your fingertips directly. And what we'll do in the next code cell is show you how you can set up a water balance for the entire model. So I have some lines of code here that identify where the file is with the output results. It is called modelname.cbc, and sorry, it has a slightly different name, but this code here inserts the model name so that you never have to think about the exact file name. So it would be mf6 webinar.cbc or something. And then you can grab the contents of what is in that file by calling this line of Python code, which opens the cell budget file. So it has this file with which, depending on how you define things for your output, but for every time step in the model, or at the end of every stress period in the model, you have information about the flows. And in this case, we have information in there about the well abstraction, the groundwater recharge, and also the flow across the boundary on the right-hand side, which is that constant head boundary or specified head boundary that represents the river. And we can grab that information from the file. There's a little function there called get data. And depending on what text label you pass with that function, you get specific information about a particular feature of the model. So in this case, the well, the recharge, and the constant head boundary. That information is stored in a list. So never mind the details, but you need to grab the first element of that list. And those are all things that we'll cover during the course. So don't worry about it now. And 0 means the first in Python. So if you're not used to that yet, that is something that is something to keep in mind. So, of course, the recharge is distributed areally across the model. So we get an array of values for every cell in the model. And in this next line here, we sum all those values so that we get the total volumetric recharge rate across the entire model. And that's the water going in. And we have also water going out, obviously, through the well. So we have to sum all the values that are stored in the well array, but also for every cell that represents the river, we have to sum the discharge that passes across the model boundary to that cell, and we sum those values as well. And those are then the net outflows. Now we have some print statements here, and I've already run this cell, so you can see the result. You can see that the total volume going in is this 12,375 cubic meters a day, and out is almost the same number. It's a negative number in this case, 12,361 cubic meters a day, and that represents a relative error that we calculated here with this formula given as a percentage. That gives a relative error of 0.11%, which is already quite good. But I also reckoned that, yeah, we can probably get a little bit closer than that. So I'm just going to go back up and illustrate that you can play around with the solver settings. And in MODFLOW 6, it can be quite, the solution that you get to your flow model can be quite sensitive to some of the solver settings. And in this case, I go back to the cell where we identified the iterative solver, and you can see that we have another parameter here, which is called the inner DV close. That is, in this case, the closure criterion for the heads. So the model will stop iterating once all the heads in each cell change by no more than 1e minus 6 meters, so 1 micrometer. So there are a lot more settings for this solver, but there's definitely no time to go through them in this webinar. I'm just going to change this. Then I'm going to scroll back down to the cell where I calculated the water balance. And just for convenience, I'm going to say run all of the above cells in my notebook. So the entire model will be generated once more. You can see that it also runs the cell where we create this output. And now we can execute the cell with the water balance calculation once more. And now we can see that with this more accurate closure criterion for the iterative solver, we also get the outflows much more accurately. So that is really a slight improvement there of the water balance error. And that was just to show how these solver parameters can matter, and we didn't pay any attention to them up until now, but it's something that you definitely need to be aware of. Okay, so we have the head contours, and from the head contours, we can already infer what the flow direction is, but you can also visualize that with the FloPy capabilities. The USGS have spent a lot of time and effort in trying to implement that into FloPy so that you can get a direct visual representation of the flow field. And one thing that you need for those are the specific discharge vectors. So those are calculated with Darcy's law, and you get them at the cell centers. So for every cell, you know the specific discharge components in the X, Y, and Z directions. And with that, you can create a quiver plot in Python that shows you arrows that indicate the direction of the flow. And it's all done behind the scenes. So in Python, FloPy, there is this function called plot vector, and you need to pass it QX and QY. And you can set the scale, and you can determine if you want to show all the vectors or just a subset by creating steps. So you show every fourth vector in this example, and you can set the color and things like that. Now you grab those QX and QY values from the cell budget file. So you need the cell get data function for that. Just like before, here we had that text label. In this case, you need the block of data that is called data -SP specific discharge. And you have to do some reshaping of the array for this plot vector function to work. But once you do that, you can see that this is the result. And I'm just going to go up to the code cell. I can't show the figure and the code cell at once with the zoom level that I'm in, but here you see that I created a loop. I'm looping over all the layers of my model. And we have 4 layers, and for each of the layers I create the a subplot with the specific discharge vectors. So this is the top layer, this is the aquitard. I'm not sure if you can see it, but on my screen, I can only just make out a couple of points there. They are the vectors, which means that in the aquitard, the horizontal flow is basically 0, as we would expect because of the low hydraulic conductivity. Then in layer 2, we clearly recognize the effect of the 3 wells. We have large vectors here, and they are the high flow velocities that we have near the well screens. And also in layer 3, which is very well connected to layer 2 because of the permeabilities, we see that there are quite high vectors there, clearly showing the convergent flow fields towards the wells. So that's one way of visualizing it. But there's also the possibility, once you have calculated your heads, to calculate path lines with another piece of USGS software, which is called Modpath. You may have worked with it, and it's always a little bit of a hassle to create the path lines because you have to define the starting points of the particles. And it's a fiddly process, but it's definitely doable once you get into it. And what I'm going to do in this next code cell is I'm going to start a number of particles around each of the wells, and then I'm going to trace those particles in the upstream direction. So I'm going to see where the water that goes into the wells comes from. And to do that, the first thing I do is I create a little function. This is a function definition in Python, and it takes 2 arguments. R is the radial distance from the well center, and N, capital N here, is 12, means I want to create 12 particles. And this function calculates the position relative to the well of those 12 particles on a circle. You can see the code there. It looks a little convoluted if you're not used to Python, but basically what you will get is a series of 12 points that are on a circle around the well center. And then I can take those values that I just calculated. I store them in this array called PR. I can grab those in a later part of the code, and I can then start placing those particles into the model. And you need to loop over the 3 wells. We had that list with the row and column coordinates or column numbers of the 3 wells. So I'm going to loop over each of these wells. This is the row and this is the column in which that particular well is located. And then you can see that I'm looping over those 12 points that I just created. And then I can define the local coordinate space where these particles are located. So this is how Modpath works. You indicate in which row, column, and layer you want to start your particle. And then for that particular cell that you indicate, you have to define the local X, Y, and Z coordinate that you want to start the particle from. It's all I'm going to say about this, because you really need to have some knowledge of Modpath to understand what is happening here. But basically, this is the idea. And you can see here, for example, local Z is 0.5, which means that we start the particle in the center of the layer. So that is what that local coordinate indicates. Then I have to tell Modpath the locations of these particles. So I define a particle data object, and I can then also define particle groups. In this case, I only have one group, but in Modpath, you could define multiple particle groups. Each group has particle data, so I have to tell MODFLOW that in this case, I have a single group with my particle data I just defined. Then I create the Modpath object. So it defines things like the output or the name of the output file, where it will store the output file, which MODFLOW model it has to use, and also which executable and where it's located. Now, for the velocities, it matters what porosity you have. So in this case, we selected 0.3 as the porosity. You have to create a basic file, a basic flow package for the Modpath executable. So that takes the porosity, but it also takes other parameters, but we're not dealing with them today. And then we have a Modpath simulation, and we can specify a couple of things. Probably the most important thing to note here are the three that we have here. Let's start with the last one. Yeah, I said I'm going to track the particles upstream. So that means that I'm going to track the particles in a backward direction. I'm going to see where they come from. Yeah, you can also do forward, but they will be sucked into the well straight away. So you will not see much in the plot that we'll create. And also we have a stop time that we specified. So in this case, we're going to track them backwards, and we'll stop the particle tracking once the travel time to the well or to the point where I start the particle has reached 100 years, 100 times 365 days. So that's what I specify with stop time option specified, and that specific stop time that I defined. Then just like for MODFLOW, I write the input, I run the model, and we'll see some output there. It takes a little while, but here we have the result. So it says that after 100 years, there are still 31 of the 36 particles active in the domain, but 5 have terminated at strong, source, and sink cells. So let's see if we can also identify them in a plot. So what we'll do is we'll create a plot. And the commands are here. So we'll create another map view with the plot map view function in FloPy. We'll contour the heads in a similar way as Mark just explained. And then we need to locate the Modpath output file. In this case, it is the file that has the extension mppth, Modpath, particle file, and FloPy has a function to grab the data that are in that file. So then you get all the information for each individual particle, and then you can loop through that information. So for each particle, you can grab, for example, the x coordinates and the y coordinates. And once you have them, you can just plot them as a line in Matplotlib. So in this case, we plot them and we give them the color C1, which is the orange color that you see here. And this is the line width. And it's just something you can choose yourself. And this is the beautiful plot that you get. And you see the blue lines, they are the heads, the orange lines, they are the path lines. And what immediately is striking is that these path lines seem to be crossing, which is impossible, of course. They cannot cross in the steady state model. So what's going on there? Well, that's because this is a 3D model, right? We're looking at this from above. So we need to also take into consideration the third dimension. And you can also see that there are 5 path lines that go towards the river, the constant head cells at the top there, and they are the 5 particles that were reported to end at strong head sinks in the Modpath output. So that's the figure. I'm not going to talk too much about the next cell, but you can also play around a little bit and give the lines different colors depending on the layer in which they're in. So you can check, the layer is also stored with the particle location. So you can grab that from the FloPy data with PIK. K is the layer number. And then depending on the layer number, you color the line. So you can see that this is layer 0, the top layer. Then it goes into the next layer. This is the third layer because it skips the aquitard, and then this one is also slightly in the deepest layer, turns red. So that is the way you can clarify things here, because as I said, you're looking in plan view to a 3D structure, 3D flow lines, and that tends to complicate things. The other thing you can do, this I think is quite cool, you can also do this, it doesn't work in Jupyter Lab, so I'm running this in Jupyter Notebook. you can also visualize it in 3D. So you can create a 3D plot in Matplotlib, and then you can also show these lines in a 3-dimensional space. And then it's really cool that you can also pan and rotate and things like that. So if you get a complicated flow field, then this is really a neat option to try and understand the flow directions and what is happening in that 3D space, which is very difficult to get from maps. So this is not standard in FloPy, but this is just using the 3D capabilities that you have within Matplotlib. Okay. Well, I'm going through this at a record pace, but yeah, rest assured that we'll cover this in a lot more detail during the course. This webinar is just to showcase all the options that we have. And one thing that is really nice in MODFLOW 6 is that you can have discontinuous layers. So that didn't exist in previous MODFLOW versions. You had to make layers very thin in that case if they disappeared. And that could create all sorts of problems, numerical problems, or problems with your transport if you tag that onto your flow model. But in MODFLOW 6, there's this neat thing called the I-domain. And with the I-domain array, you can indicate if a layer is in the model or not. And in this case, we're going to use it to see what is happening when there is a hole in the aquitard. So you can grab, you can define polygons. And in this case, we just defined one by hand, but you can also import it from a shapefile. And then you can intersect that polygon with your grid. And from that intersection, you can determine which cells are located on top of that hole in the aquitard. And then you can set the I-domain of those cells in the appropriate layer to -1. And then MODFLOW 6 will understand that that layer is simply absent, so that there's a direct connection between the top aquifer and layer 3, the top layer of this of the underlying aquifer, and the whole aquitard will be bypassed in that part of the model domain. So yeah, I'm not going to say too much about this. We have the polygon, which is defined by a couple of vertices. And then we will use the intersect functions that are in FloPy. I think it was Artesia Groundwater here in the Netherlands that did a lot of work on these routines. And they did a marvelous job. And then with this particular piece of code, nothing happens. You can't see a thing, but it intersects that polygon with the model cells, and it determines which model cells are below the polygon. And I can probably best visualize that. Here you can see the result. So this is the polygon that we defined. It had 4 vertices, and you can see the structure of the grid below. So all these cells that are within the polygon have been identified as where the hole in the aquitard is located. So if I now want to incorporate that into my MODFLOW model, all I have to do is change the discretization package. Because that I-domain array that I mentioned is part of the discretization package. And before we didn't worry about it, we just assumed that it was default, and that in the default, all cells get a value of 1. So what we can do in this case is we can set all the cell values to 1. We use the ones function from NumPy to do this. And then we look up the result of that intersection, which was up here. But we loop over all those cells that have been identified as being within the polygon. And for all those cells, I'm going to, I know the row and column number, and I need to set the second layer, that is the aquitard, I need to set the I-bound value to -1. So in that part, the aquitard is absent. And now I get a warning, this package already exists. I'm going to replace it with I'm going to replace the existing package. FloPy tells us that's exactly what we want. So that's good. And then I'm going to rerun MODFLOW. There you go, I get solved successfully. And we've seen this before, the contouring of the heads. Here they are in a new plot, and you can see the polygon that I just drew before, and you can also see the head pattern. You can still clearly identify the 3 wells, but what you see happening here is that in the area where the aquitard is absent, the head contours, they almost overlap. And that is because the heads in the top aquifer and the aquifer below it now become almost the same, because we have removed that resistance, that hydraulic resistance that is provided by the aquitard. So here you will probably see an area where the water races through from the top layer down to the bottom aquifer on its way towards the well, because this is where the hydraulic resistance is lowered. Just going to check that by calculating the flow paths in exactly the same way as before. And now I visualize them in 3D. And what do I see? Well, it's a bit hard to see, but this is where the hole in the aquitard was. And we can see that indeed, this is the area where a lot of the water is just going down from the top aquifer to the aquifer down below the aquitard where the wells are. So it provides this window for preferential flow. Then finally, this is the last example. What if you have a transient simulation? So what if things change in time? Yeah, obviously, we have a well that is switched on, and then during the initial stage, we will see a lot of drawdown increase around the well. So we'll get a cone of depression. The heads around the well will drop, and we want to visualize that in time. So how do we do that in MODFLOW 6? Well, before we didn't specify anything about the transient behavior, but all we need to do to incorporate that is to invoke the storage package of MODFLOW 6. And that's done in this code cell here. So we have the MODFLOW storage package, STO, and then it's coupled to our existing groundwater model. We don't need to make any changes to that, except for the time discretization, which I'll show in a second. We define a specific storage coefficient, in this case, a single value for the entire model. And we tell MODFLOW that this is now going to be a transient simulation. And if we didn't do that, it would simply be a steady state simulation. So I run this code cell, and here you can see that I will also update the time discretization. When you have a steady state simulation, doesn't matter what you input as the time discretization, at least not for the calculations. It may for the output, but for the in general, it doesn't matter. But for the transient simulation, you have to think, of course, what stress periods would I like to specify? And here I specified 3 stress periods. The first one is very short, because right after we switch on the well, there will be a fast head drop at the well. So it's only 100th of a day, and it's subdivided into 10 steps. And this is a multiplier, but we set it to 1. And then we'll simulate the next 900th of a day. So we end at 0.1 days. And then we have another 0.9 days that will simulate. So at the end, the cumulative time will be 1 day. So this is how I discretize the time. And then I have 3 of those stress periods. And I pass the time information to the period data argument of the MODFLOW discretization package, time discretization package. It also replaces that one. And now it's calculating. You can see it takes a little longer because it has to calculate these 27 or 28 time steps that I just specified. And then the final thing I will show you is how you can then plot that as a hydrograph, that model output as a hydrograph. So now we have, again, a file which contains the heads, but now there will be multiple times at which there will be output in that file. And for every time step in each stress period, there will be a record with output values. And we can read that in. And there's a lot of redundant information there just to make the plot pretty and things like that. But this is the code that really matters. You can use the get time series from FloPy, and it allows you to specify a set of layer, row, and column values so that identifies the cell at which you would like to grab the time series. So in this case, I'm looping through the well row call list. So I'm getting the rows and the column indices of the wells, and I want to plot a time series for the head in the top aquifer. So I indicate layer 0 there, that's the top aquifer. And then I plot the information that is in there. So I get an array which has the time in the first column and the heads in the second column. So I'm using the plot function to plot that. And then the layer below aquifer, the aquifer below the aquitard, that's layer 2, and I do the same. If I run this, I get this plot. Yeah, scroll down a bit, thanks. And you can see the result here. So remember that we had 3 wells, and well 0 was the northernmost well. That was located directly below the, or closest at least to that polygon that we defined with the aquitard window. You can see that the heads between the 2 aquifers are different, but not so different. At least they show the same behavior in time, and there's a bit of an offset between them, but they're relatively close, especially if you compare them to the other 2 wells. If you compare the orange line for well 1, which is in the middle, to the orange line for the top aquifer, which is here, and the orange line for the bottom aquifer, they are separated by many meters, and this one here by a couple of decimeters. So here the head difference is very small because there is not that aquitard, and here the head difference is much larger. So yeah, this is another way of visualizing your model output as head drawdown or head time curves or drawdown time curves. And it's all possible in FloPy. Now we went through this in record speed, and we went 3 minutes over time. I hope that's okay. But yeah, if you're interested in doing more of this and doing it at a slightly more agreeable pace, then obviously you're very much welcome to join our course, where we will go over this and also other examples of how to use MODFLOW 6. You can also look at unconfined flow. We haven't talked about that yet, but that's something that we'll be discussing then as well. So I hope, despite the pace, it was pretty much clear. I don't know how things look in the Q&A. Were you able to keep up, Mark?
I think I kept, yes, I think I was able to keep up and was able to answer most questions.
You've done well, done extremely well. But why don't we have just a couple of minutes where we've gone past the 1 hour mark, and you've just made coding the magical mystery tour no more. It is now much clearer. I'd do coding if I had lecturers like Mark and Vincent. Well, that's really what we want to remind you of, is that tomorrow the early bird for this course cuts off. Early bird costs, the fees, the prices for early bird are finishing tomorrow. But the course on the 10th of November, I couldn't push it more highly. These gentlemen know what they're doing from a long time ago, and they're not paying me to say it. Let me tell you that. I just love what they're doing. But I agree. If we've got 5 minutes, you might want to review some of the questions, Mark or Vincent. Up to you. You might want to look at the Q&A. If not, that's okay too. But have a quick look through those questions. Pick out ones you think were really crucial. Otherwise, we'll close down within a few minutes.
Yeah, well, there were a lot of questions. So what FloPy can do, right? Can we use shape files to import stuff? And the answer is yes. And we'll show examples of that, right? What if you have a DEM of your top of your aquifer? Well, you can just use that. For this simple example, we made it flat, but of course we know in reality it's not flat. And if that matters to your problem, then you can definitely use that. Same for aquifer layers, right? If you have a nice geologic map or a digital map of that, then you can put all those in there. You can vary the hydraulic connectivities and read those in from shape files. And you can also output stuff from FloPy into shape files. If you are more comfortable to do your visualization in the GIS or make very professional figures in that, then all those capabilities are there. And we'll touch upon some of those in the workshop as well. There's been a massive revolution in what models can do in these last 20 years that I've been looking at it. And this is just there seems to be the pinnacle of what can be done. No holds barred,
Yeah, maybe I'll add just briefly to that, because when Mark and I started to develop FloPy, we felt restricted by the capabilities of some of the GUIs, the graphical user interfaces. And I'm not sure if it has been touched upon in the Q&A. I was just browsing through, but there's so many there that
Yeah.
It's hard to take it all in. But the other thing is if you have time variant boundary conditions. So if you have a well that switches on and off, maybe you have 30 years of pumping records that you need to input into your model. If you can just read them from an Excel database and plug them directly into the well package with FloPy, that is so much easier than that you have to copy that data over into a graphical user interface. Sometimes you even have to type it manually, and you bypass all that complexity if you master FloPy. And that was also one of the original reasons why we started to develop it, just to have that complexity, or that ability to add that complexity, but keep it very simple. Yeah, at least the process of putting together the model.
Right. A couple of questions maybe to finish off with from Phil Hayes. You'll see there, great presentation. One question, can you comment on the differences in levels of integration between FloPy for USG and MF6, MODFLOW 6? Comments on that?
Not sure if I can see the question.
It's cute, the Phil Hayes question at the top there on the Q&A.
There it is, yeah.
Yeah.
Yes, yeah. Well, so the interesting thing is that MODFLOW USG, it's a very detailed question, Phil, but MODFLOW USG and MODFLOW 6, they kind of exist next to each other. And there are some capabilities, some new capabilities in USG that have not made it into MODFLOW 6 yet, and may not make it into MODFLOW 6. MODFLOW 6 is done by the USGS, and MODFLOW USG is done by Saurabh Pandey and his group, and I'm also working on that part. So there are some differences between those two models, but MODFLOW 6 is the standard USGS model, so that's what the workshop is going to be about, and we're going to try to use that. And if there's capabilities in USG, we might refer to those if we can. But they exist next to each other.
Well, that's excellent, everyone. I'm really enlivened by this. So was everybody else going from the comments. Thanks so much, everyone, for your fantastic questions. A real robust discussion going on there in the background. Any other comments now from either yourself, Vincent, or Mark, and I'll close the webinar. All good? Any last
All I would say is
wisdom?
Thank you for attending, and hopefully we've given you some ideas of how you can use this in your day-to-day workflow.
Yep. Sure.
Yes, I hope to see many of you in the course next month.
Yeah, do that, absolutely. There's a recording of this webinar coming to you in the next day or so. It will be uploaded to the website and the YouTube channel. As a live attendee, you will get a certificate of attendance within the next 2 days. This can go towards your continuing professional development hours. And finally, really importantly, at the end of this, a 1-minute survey will pop up automatically. Please take 1 minute. 1 minute survey takes 1 minute, and give us your thoughts. That'd be great. You can see there we're doing live webinars, live courses. We're doing webinars, and we're doing on-demand courses and standalone courses, on-demand series and standalone courses. I won't go into the detail. There is just so much going on here at the Australian Water School. We are delighted you could join us today, and great thanks to yourself, Vincent, and yourself, Mark, and also to Joel and Renee, without whom this couldn't happen at all at the Australian Water School. Thanks, everybody. Wonderful time together today. Thank you.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.